Today's lecture, we are going to be covering two topics. Both of it is not covered in the textbook and it will not be part of the final exam. So I've just recorded this video outside of class hours so that it's available to you once the semester is done. You plan on working in the electric drive sector. These two topics would be quite helpful. So I figured I should record it and put it on Canvas. So in the future, you'll have access to this resource if and when you choose to learn about it. So we are going to cover two topics today. The first one is addressing one of the commonly occurring confusions for people when they work with permanent magnet synchronous motor is the three different terminologies that I used. One is the torque angle, the other one is the load angle, third one is the power angle. These three terms mean different things, and there's quite a bit of confusion between what those terms mean because different textbook addresses different one of these angles without providing too much of a complete context to it. And that caused a little bit of confusion what the terms mean, which point is stable, which point is unstable, so on and so forth. So for instance, all the lectures that we have done, we have always spoken about torque angle. That is the angle between the BMS space vector and the BR space vector. And that is the same thing that's used in our primary textbook, Prosonate Moments textbook. And throughout the textbook everywhere, that's the only angle that's ever discussed. But if you look at the other two textbooks that we have, both Krauss and Fitzgerald, for Fitzgerald instance, in chapter 6, chapter 4, they define delta as the angle between the BMS space vector and the BR space vector, same as it's in your primary textbook. But once it goes to synchronous generator, rightfully so, they start talking about the angle between the EMF space vector and the voltage space vector, in which case it should rightfully be the power angle. But in all of these cases, it's usually called as delta, and that's the cause for concern. And particularly when you go to the advanced electric drives course, which I'll be teaching next semester, we would be more interested about the angle between the state of flux linkage space vector, which is another term I haven't introduced just yet in the class, and the rotor magnetic field space vector. And this angle delta, the load angle, would be very close to the power angle in most cases. And that is where most vector control textbook would refer to that angle as the delta and that angle being the load angle. So because of this, there's a bit of confusion which we'll try and clarify today. And the second topic that I want to talk about is modeling a permanent magnet synchronous motor using numerical simulation software, either MATLAB or Simulink, whatever your choice is. So here, when we go to, again, the advanced sector vector control course, we would use a different reference frame called a DQ reference frame to model it. As I model the PMAC motor, I'll give you a brief insight as to what the DQ frame of reference modeling would be. But we will be doing it in ABC domain. As far as permanent magnet synchronous motor is concerned, both of those models do not give you any difference in the performance or the stability convergence and so on and so forth. But when we do an induction motor model, we can theoretically show that the DQ model is more numerically stable compared to an ABC model. But as far as permanent magnet synchronous motor is concerned, it really doesn't matter. So that's the second part, we'll do that modeling. And the first part, we'll be doing the difference between these three angles. So the first of the two extra lectures that I'll be recording, towards the end of the semester, I'll record one more extra videos and I'll post it towards the end of our course recording videos. And that'll be on the topic of torque production in a one-phase induction motor. And we'll also briefly discuss about some generator action and so on and so forth for a three-phase induction motor as well. Okay, with that, let's get started. Okay, so we have so far derived the expression for a torque in our motor, electromagnetic torque, and that expression was pi times R times L times Ns divided by 2 times the magnitude of VR times the magnitude of the IS space vector times sine of delta, which is the angle between the rotor magnetic field space vector, which is basically the direction along which the rotor magnetic field is its maxima, and the stator current space vector. Again, for stator current space vector, we have looked at multiple interpretation of what that means. None of them physical. In sense of the conductor distribution, we figured the stator current space vector points to the direction where the conductor density of the all three phases combined would be at its maxima at any given particular time. Right, n times I product for all the three conductors combined together, carrying three sinusoidally phase shifted current. That was one interpretation. The other one we saw was a geometric interpretation where we had three independent variables and these variables can occupy every single point in the 3D space if they are truly independent. But in a three-phase system, in a balanced system, the voltages would have to be such that the sum of the voltages is zero. Even if it's an unbalanced system, if there is no neutral wire, the current, sum of the three currents would have to be zero. So in those cases, when sum of three variables are equal to a constant, in this case the constant being zero, x plus y plus z equal to zero, that's an equation of a plane. And the space vector transformation is basically a rotational transformation that rotates things around. There is a third way of interpreting the space vector transformation as well, which is if you have your stator current space vector, and marker is now working. So our stator current space vector was IA e power j0 plus IB e power j2 pi by 3 plus IC e power j4 pi by 3. And all of these are time varying currents. And you plug it into the equation, you get a space vector result. And you can think of this as a weighted sum. So when you do averaging and you want to give lesser weight to some values and higher weight to other values, you would give some weightage to the set of values that you have. This you can say, I want to take 50% of this, 25% of this, 25% of this. And we have all had done vector summation in many of our classes, the weighted summation in many of our classes. So this is doing same weighted summation, but in this case, typically when you think of weighted summation or weighted average, you would use weights which are scalar values. If I had 50%, this will be 0.5, this will be 0.25, and this will be 0.25, which you will multiply with IA, IB, IC, and then sum them up, divide by 3 to get the average. But there is another way of doing this as well. Why restrict ourselves to just scalar weights? We can use vector weights. In this case, we are using a vector, a unit vector, the scalar magnitude of the vector is 1, but we are putting weights along different directions. In a scalar case, we are putting weights along one direction, but different magnitudes. In this case, in a vector case, we can have different magnitudes and different directions. We are choosing to have the magnitude same and having different vector directions through which we are weighting these three values and then summing them down to have a vector weighted sum, which is the space vector transformation. There are multiple other interpretations for space vector transformation, many beautiful mathematical ideas that can be scoped out of this particular expression. But for now, we'll leave it at there. It can be a separate lecture in the future to look at all the other ways of describing the same thing. Okay, so we have our torque equation, and this again we saw basically comes from the fact that it is equivalent to some stator current space vector cross product with the rotor magnetic field space vector, and very reminiscent of what we have with our Lorentz force equation, R cross F, and F itself was L times I cross B, and this is this pi times L. This is some equivalent length, and then ns by 2 is the number of conductors that we have. Very similar to what we have with the Lorentz force equation, with some scaling factor that we have, the pi term, because of the fact that the distribution is sinusoidally distributed. If the conductors were all the same number on each of the slots and they were all carrying the same current, then this pi factor would have come into your contribution factor. As we determined in case of a DC motor, where the torque equation just came out to be NC divided by M times L times I cross B. So we have gotten something similar, but the pi factor comes from the sinusoidal distribution of our winding. And then we went ahead and drew the space vector for this. So let's say our currents are, let's give some values to it. IA is some Im magnitude, cos omega Et, where omega E is the electrical frequency, 2 pi times F, whatever the grid frequency is, if it's a grid connected motor. Im cos omega Et minus 2 pi by 3, and then IC is cos omega Et minus 4 pi by 3. And for this particular set of given currents at time t equal to 0, the A phase current would be at its maxima. So our current space, our space vectors that we drew, our current space vector was here at time t equal to 0. And then our BMS space vector is along the same direction. Our rotor magnetic field space vector can be at any direction, BR space vector. And the angle between the BMS space vector and the BR space vector, or BR space vector and the IS space vector, is what we call as delta. So since we are going to talk about three different angles, let me give a subscript to this, delta tau, where delta tau is the torque angle. Right, so coming back here, delta tau is the torque angle. It's basically the angle between the BMS space vector and the VR space vector, or it is same as saying the angle between the stator current space vector and the VR space vector. So again, to clarify what the BMS space vector is, this is the magnetic field in the air gap. In air gap due to IS alone. No contribution from BR. This is a very particular important point because a lot of people get confused about this. I've even had comments from some people who have said that the textbook has gotten the expression wrong because they always think about power angle, but not this angle, which is between BMS and BR. We look at what the power angle expression comes to, and the power angle would be completely different from the torque angle that we have here. And the term load angle itself is used interchangeably to describe both, which is where a lot of confusion comes from. But the textbook sticks with this notation, while most other textbooks which are on vector control would typically stick with the power angle description, and that's where a little bit of confusion comes from which expression is correct. But the textbook, Prasanna Mohan's textbook definitely has the expression correct though. So you go back and take a look at the textbook, and it differs from what's given in other textbook. For 100%, Prasanna Mohan's book is absolutely right. Okay. So we have this. This is what we had before, and then we had our EMF space vector, which was 90 degrees ahead of the VR space vector. So this was our EMF space vector, stator EMF. Let me put a subscript to this EMF due to VR. Right? So the EMF induced on the rotor coils, stator coils, due to the varying magnetic field of the rotor as the rotor starts to rotate. So this is what we have, and we saw that from that expression on the left, if IS magnitude is a constant, how do we achieve that? We connect our motor to some kind of power electronic drive, and we've already seen how we can do current control in case of a DC motor. In case of a permanent magnet synchronous motor, we would use something very similar. When we go to the advanced electric drives, we would, instead of looking at these, right now we have these currents that are varying in time, but we already know how to design a current controller to control the current of a DC motor. But the only requirement there was the currents where it's steady state DC value. And then we could design some kind of transfer function, analyze it, and design the KPK values, which we have done numerous times now. We can do something similar for a permanent magnet synchronous motor, but the only problem is the currents are varying sinusoidally. So how do we design a controller for it? You can keep it in sinusoidal domain and create controller, but it gets a little bit complicated choosing the bandwidth because you're limited by on one end you'll be limited on the bandwidth by the frequency, fundamental frequency of your electrical frequency that you have, omega E. And when you want your motor speed to change, that omega E changes. When you design controller, you want to choose bandwidth that are restricted in value that do not vary all over the place. So we can still design it like when we do V by F control in the beginning of advanced electric drive, we do account for the varying electrical frequency and still design a controller, but the performance of the controller will be very poor compared to what can be achieved otherwise. So what we instead do is, here is a particularly good insight on what's actually going on, because if you look at the space vectors, the currents themselves are varying sinusoidally, the phase currents, but the space vector magnitude is a constant for a given magnitude of the input currents. Even though in time the currents are varying sinusoidally, the space vector magnitude is a constant value. And if the input current magnitude moves around slowly over time, then the space vector magnitude also changes, but it's still a DC quantity. You do not get sine waves out of the space vector. So that's the idea that if you look at the space vector, these are all rotating at some speed, which is basically the synchronous speed. And instead of looking at it from a stationary reference frame, if you were to look at it from a rotational reference frame moving at the same speed as the space vector, all of these quantities are DC entities. So instead of controlling your actual stator currents, if you were to control the space vector that is created, then you have DC entities. You can create PA controller just as you have done for a DC motor. It behaves exactly like a DC motor model. And then you can create your KPK values, design everything, control your space vector. And we know it's a 1:1 transformation that we have already shown before. So if you control the space vector current magnitude, then you're controlling basically the three-phase currents as well. So that's what the whole of the advanced electric drive poses, just going on to a different reference frame and simplifying a little bit more complicated problem. Right? So in case of maintaining this current a constant in the basic drives course, we don't worry about it, how it happens. But the idea is basically we have a similar control mechanism that we have on a DC motor, and then keep the control the current space vector so that the space vector magnitude is a constant, but the phase current themselves varies in time as a function of the electrical frequency omega e. So given a constant magnitude of the input current, then the torque, electromagnetic torque, all the other terms there are constant. Pi times R times L times Ns divided by 2 times your Br. All of these are constant. Now our stator current magnitude is also a constant. Right, so all of these are constant. And the only thing that remains is sine of delta. And let me put the subscript going forward, delta tau. So the stator current, you should be quite careful. So this is the coil and the current in the coil. For a two-phase motor, the two-pole motor, it doesn't matter. Current in the coil is same as the current in the terminal. But when we go to polyphase, when I model it, I'll make this more clear what the term is. We have already done this in the previous lecture, but I'll go over it again once more when we model the motor. But this is the current going in each of the coils. So if you have 6-pole pairs and the 3 coils are connected in parallel, then this would be the terminal current divided by 3, because the current would branch into all of those 3 coils equally. So it will be a factor of 3 divided. But if those 3 coils are connected in series, then the terminal current coming into the motor is same as the current in each of the coil. Right? Then there will be no division factor. So given all of these are constant, this is the only term that varies, and we can plot that as some the torque angle delta tau, and then the torque that is generated tau em. So again, this is very important. I magnitude is fixed. If that is not the case, then a whole other set of equations come about, which we will see, which will describe the power angle. But this is the case where the drive maintains a constant current. And when that is the case, depending on where the load torque is, let's say the load torque, let's say this peak is some 5 Newton meter. And let's say the load torque is about 2.5 Newton meter at this particular instant in time. So the motor at steady state will settle to this angle delta tau 1. So this will be the torque angle at which the rotor would settle down at. That is basically saying the angle between the rotor space vector right here in this diagram. So the PMAC space vector is going in this direction. The rotor space vector is slightly lagging it by an angle of delta tau 1 that we have on the other side of the board. Okay. So now if we apply, if the load torque suddenly changes, so initially the load torque was like this, and then at some time it changes to a new value and goes to a new value tau L2. Then this new value would be somewhere here, and the corresponding torque angle would be this new value. Now, why does the torque angle increase as we increase the load torque? Because as soon as you apply a step change in the load torque, the power at the output, P mechanical, tau em times the omega. Because of the inertial element, the omega is not changing suddenly. And because of the inductance in the stator, tau em is not changing suddenly because the current can't change suddenly. So now we are in a tough spot where the power electromagnetic and the mechanical power is the load torque times omega. Right? So this term is not changing suddenly. This term, because of the inductance, because of Lm plus LLS, the leakage inductance. And this term is not suddenly changing because of the inertia J, but this term has suddenly changed from a lower value to a higher value. So what happens to the power? The power would also change as a step value. And now this increased power demand is not coming from the electrical system. There is a deficit between the load torque versus the electromagnetic torque. So that increased power is going to come out from the energy stored in the inertia. It's going to draw out of the energy in the inertia. So the energy in the inertia is half j omega square. And as we draw out more energy, the energy goes down. The only way the energy can go down, this is a constant, this is of course a constant. So the only way the energy can go down is by having the speed go down. And now as the speed goes down, the rotor starts to lag behind. And previously the rotor was rotating at some 2 pi times 50, let's say 2 pi times 60, 120 radians, 125 radians per second. Now it would slightly dip, it will go to 119 radians per second. So going back to our example, if you and your friend are running in synchronous, and suddenly somebody tugs on you a little bit, then you're going to fall behind. But that's only temporary. You're going to recover back up again and start running. Or a better example would be the two vehicles towed one with another. If something suddenly happens to the second vehicle, the speed will slow down temporarily. The time between the two vehicles will stretch out. But since these two vehicles continue to move, whatever the speed at which the first vehicle is going is the same speed the second vehicle would have to go at steady state. Otherwise, the band connecting them would stretch out and fail. So the same thing is going to happen here. And the equation is exactly stated. So the speed would start to come down. If the speed starts to come down, you're lagging behind. So the separation between you and your friend in the case of running or between the two vehicles tied together is going to increase. And it's going to go to a new point where the torque generated, the electromagnetic torque generated at this new point is equal to the load torque that's being requested and can be sustained at steady state. At steady state, it will go and reach to this new point that's around there stably. And the speed at which it will rotate at this new angle would be again the synchronous speed. We already saw if the rotor rotates at any speed other than synchronous speed at steady state, the net electromagnetic torque would be zero. So at steady state, if you want continuous torque production, the rotor must rotate at the same speed as the synchronous speed or the speed at which the space vectors are rotating times 2 by p. Okay? So it'll go to the new point, but in between it will oscillate, do a little bit of oscillation there and then come and settle down at this new point. Now, if we keep on increasing the load torque, we can keep on increasing the torque angle until we get to the point where the torque angle is equal to 90 degrees. Again, this is for a fixed current. And the drive is continuously providing a fixed current. If you have a permanent magnet that's directly connected to the grid, that won't be the case. The current is not being maintained a constant. You need some kind of drive that ensures that the current is constant. This is what will play out. Now, if you increase the load torque any further, after reaching the maximum value, let's say you demand more load torque, that means there is a deficit between the load torque and the generated electromagnetic torque. Because of this deficit, there is going to be a power demand in a mechanical system which is higher than what the electrical system can provide, which means it will draw out of the inertia, the speed will come down. And once the speed comes down, we already saw the logic, the angle would start to lag further, rotor would start to lag further, and it will go settle down into a new load angle. But the problem is this new load angle actually generates lesser torque, lesser electromagnetic torque. So the new tau em is lower, much lower than the load torque than it was before where it was at its peak value. That means there is more deficit between PEM and PMAC. That means more energy is drawn out of the inertia. That means it slows down even further. That means it starts to lag behind even more rapidly. It will go to a lower angle, which makes this even worse because it produces even more load torque when you need actually more higher torque, the deficit increases, and then this happens until it comes to a complete stop. Right? So this is what would happen. So the left half of it is stable, and the right half of it is completely unstable at steady state. During transient, you can go over the other side and come back and oscillate and then settle back. During transient, it's fine if you go past the 90-degree angle. There is something called an equal area criterion, which you won't worry about. In power system course, you'll learn about it. But as long as certain criterions are satisfied, the swing can be good enough. It can come back and settle down at steady state. But at steady state, it can't exceed 90 degrees. During transient, when you do simulations, it can exceed 90 degrees, nothing will happen. But it should come back and settle down. Again, this is only for a fixed current. If the current is allowed to vary, as I'll show in a minute, this angle can get well past 90 degrees. Okay? Alright, so why is this particular value important for us? Because if you come back to our equation here, so right here, so our torque is again some constant times your current, phase vector magnitude times sine of delta. Now our objective is to run the drive as efficiently as possible. For particular, like when you have drives in electric vehicles where it's run off of a battery, efficiency matters. Every single percentage matters quite a lot because it's a lot of money to increase the capacity of a battery. So if you want to run a motor efficiently, you want to have as low a current as possible to generate as high a torque as possible. Because higher the current, you have multiple losses. You have the core losses, hysteretic and eddy current losses, as well as the copper losses, I2R losses from the stator resistance. So if the current increases, those losses increases. So you want to keep this current as low as possible to generate the maximum amount of torque you want. So if you want your tau em by Is to be max, then sine of delta must be max, which happens when delta equal to 90 degrees. So in a perfect case, you want to run this with an angle of 90 degrees between the rotor magnetic field and the stator current space vector or the stator BMS magnetic field. And when we have drives, we can do this quite easily. You know where the rotor position is. You will typically have an encoder, some sort of encoder, which will tell you the position of the rotor. And you would mount it such that the position absolute zero would be pointed along the direction where the rotor magnetic field is its maximum. So you know exactly where the north pole of the rotor magnetic field maxima is at any given time. And then you would have your drive inject currents into the motor such that the space vector is 90 degrees away from DR. So what you would do is first you would start off with measuring the rotor position, which would tell you where the rotor magnetic field position is, rotor magnetic field space vector is pointed to. Right? Measure position. And then the second thing you would do is you would inject current such that the current space vector is 90 degree away. So inject IV 90 degree away from the DR space vector position. And the way we would inject that is create three currents in the stator such that the space vector end up being 90 degree forward. It's a little bit of a trivial math problem to solve and figure out what those values are. So this is what we are going to do to ensure that the drive is running at its maximum efficiency. So now let's look at what power angle is, whether this angle is the maximum angle that can be between the BMS and the VR for the motor to run stable. Let's look at another term, power angle. For that, let's quickly look at the equivalent circuit that we have seen for the permanent magnet synchronous motor. So this is the per phase steady state equivalent circuit. You apply some terminal voltage, you have some stator resistance, you have some leakage inductance, you have some magnetizing inductance, which in itself is 3/2 times L itself. And then you have some back EMF that's created across the state coil. Before we try and solve for this little bit of complicated circuit, let's simplify it a little bit further. Those of you who have done the power system course, you would have seen this very common arrangement where you have two buses, each of it is a voltage source. Let's say this is some voltage source at some phasor angle 0 degree, and let's say this is another voltage source at some other phasor angle lagging by some angle negative delta, and there is some transmission line impedance that's separating those two. And for now, just to simplify it, we are not going to assume that we are going to assume this transmission line has no resistance and it's only purely inductance on the transmission line. So you have J omega E, some inductance L, basically the reactance is some X. And you know the power equation, basically the power going from this generator to this generator is given by V times E times, here is the magnitude, the angle component, divided by the magnitude of the impedance, in this case purely reactance, let me call it XL, times sine of delta. So there's an equation that you all have seen. It's quite trivial derivation. So we have a voltage source, so the current through the reactance is going to be equal to V angle 0 degree minus Z angle. If I put the, forget the absolute sign, just remember that it's always there. It represents the magnitude, lagging by some delta, divided by J times omega E times L. This is going to be a current, and if this J goes to the numerator, that would give in part a negative 90 degree angle minus E angle minus delta minus 90 degree divided by omega EL. So the real power going from the first generator to the second generator is going to be equal to the power, real power is going to be the real part of V times I conjugate. And this will of course be the same as the real part of E times I conjugate because there is no resistance in between. So both the powers would end up coming out the same. So you can either substitute for E or substitute for V and solve. You'll get the same answer. Let's start with, let's do it with just V. So let's consider this equation. Real part of because there is no resistance in this transmission line. If there was a resistance, then the power coming out of the generator won't be the same going into this bus, because there is some amount of power lost to the resistance in between. We are looking at an ideal case where the transmission line doesn't have any resistance, purely just inductance. So let's substitute V times I conjugate. Conjugate is basically making the angles 180 degree off. So V times, this is V angle 0 degree times V angle negative 90 becomes positive 90 when you do the conjugate, minus E times angle plus delta plus 90 degree divided by omega E times L. So this is our current term, current conjugate term, and this is our voltage term that we have. So this and this. So once you multiply those out, you have the real part of V square. The angle will be 0 plus 90, 90 degree positive, divided by omega EL minus V times E times angle of delta plus 90 degree plus 0 degree divided by omega EL. Now real part of this term is just going to be equal to 0, because if you take the represented in the Euler's form, this would be some V square divided by omega EL times cos of 90 degree plus J sin 90 degree. Cos of 90 degree is 0, you're left with J sin 90, J sin 90 is just J, so this whole term is just imaginary, so real part is 0. You do the same thing for here, you will have cos of delta plus 90 degree plus J sin delta plus 90 degree. So the J sin delta plus 90 degree is the only term that will survive. Sorry, the cos of delta plus 90 degree is the only term that will survive. The J times sin of 90 degree plus delta would not survive, because you're only interested in the real component. And there is a negative sign that's there as well. So let's pull that negative sign out. So it's the real part of V times E times angle delta plus 90 degree divided by omega E times L. This again you can represent it as cos of delta plus 90 plus J sin delta plus 90. Now this is purely imaginary, so the real operator will eliminate it. We have cos of 90 plus delta, which is same as negative sine of delta. This negative and the negative outside gets cancelled. All you're left with is V times E times omega E times L is the reactance, right? The magnitude of the reactance times sine of delta. So that's how we get this angle for the power expression. So what this says is that we have two voltage sources separated by some reactance, some inductance value. Then there is going to be power flow between them depending on whether this voltage source is leading this voltage source or this voltage source is leading this voltage source. Depending on which is leading it, that is going to send the power. The other one which is lagging is going to take the power in. It is somewhat a little bit confusing for those of you who see this equation the first time, because when you have a DC network, right, the power always goes from the voltage source that has higher voltage to a voltage source that has lower voltage. If you have a battery that's at 9 volts and another battery that's at 8 volts and you interconnect them, the battery at 9 volts will supply power to the battery at 8 volts. That's how it will work. Doesn't matter what the capacity of the second battery, it could be 100,000, let's say 5,000 ampere hour. Right? The other one could be just a 10 ampere hour. Doesn't matter if it has higher voltage, it's going to transfer charge to the battery with the lower voltage. That's how it works. But in an AC circuit, that's not how it works. This could be a million volts. This could be 1 volts. But there could still be power going from the higher voltage to the lower voltage if this voltage angle leads this voltage angle. Right? So in an AC circuit, it works a little bit differently. Come back to our equation here. Now we can extend the same thing for our permanent magnets motor as well. So if you look at the equivalent circuit that we have there. So in this and this have exactly the same form, except if you ignore this resistance term. If you make an assumption that the resistance is small enough, then we have some terminal grid voltage which is fixed. We have some back EMF which is coming from the motor, which at steady state is going to be fixed because the frequency of this grid voltage is fixed. The voltage that you apply on this terminal, let's say it's 60 Hz, then the electric frequency is 2 pi times 60. Once that's 2 pi by 2 pi 120 pi, the frequency, the speed at which the rotor would rotate, if it's a two-pole motor, would be 125 as well at steady state. If it is a four-pole motor, it will be 65. If it's a p-pole motor, it's going to be 125 times 2 by p. Right? So the rotor speed is fixed. If the rotor speed is fixed, then the back EMF term is fixed. Because I have put the derivation in the notes, I will write the equation again this time when we do the model. But the back EMF is also fixed, given a rotor speed. So this term magnitude is fixed, this term magnitude is fixed. Only the angle of the back EMF can change the delta. So this becomes the same case as what we have here. We have some voltage source on this side between some inductance in between. In this case, it was a transmission line inductance. In this case, it's due to the stator coil winding inductance. And let's ignore the resistance for now, just to keep it simple, but we'll address that assumption in just a little while. So in our equivalent circuit now, ignoring the resistance, and let me combine both the inductance together. LLS plus LL. Let's call it the total stator inductance LS. We have some back EMF, we have some terminal voltage. The power itself is going to be V times E times sine delta divided by omega E times Ls. Right? Let's say at some frequency omega E. So the speed at which the back rotor would rotate, omega mech, would be equal to 2 by 2. I already have it as omega E times 2 by P. The electrical frequency that this back EMF induces, the frequency at which this EMF would be induced at, would be the mechanical speed times P by 2. So it will be the same frequency, omega E, which is the same as the electrical frequency. In an AC network, if you have two different frequencies, you can never reach steady state. Unless they are multiples of one another, in which case you can still reach some kind of quasi-steady state. But if they are non-multiples, which would be the likely case if there is random speed, then there can be no steady state situation at all in that particular case. So for that requirement, as well as the way the motor operates, as we saw last time, if the rotor is rotating at some 65 radians per second, we did see that the electrical frequency for a 4-pole case would be double that, because every half rotation, the stator coil see one full sweep of north to south pole. Okay, so it rotates at twice the speed at which the mechanical speed will rotate to get a 4-pole motor. Okay, so let's look at this equation and see what this means. For a given frequency, let's say for the given voltage, markers are all bad today. Oh, this is much better. So we have, so this is, sorry. Let's say V is fixed. For instance, think of it as a grid voltage. And then E is fixed as well. E magnitude is fixed because omega E is fixed. And the EMF is directly proportional to omega E. And since omega E is fixed, the back EMF term is also fixed. And then of course Ls is fixed. Again, we are not going to assume saturation or anything like that. If there is saturation happening in the core, then Ls would vary as how deep the saturation is. If it's well into saturation, typically for drives, a well-designed drive would reduce its inductance by a factor of at least would be anywhere between 60% to 30% of the zero current inductance that you would measure. So the inductance would go down quite a bit. But in our case, for simple analysis, we are going to assume this to be fixed as well. Omega E is also fixed. So everything there is fixed. The only variability is sine of delta. So we can do the same thing here that we did for the torque curve. And if you look at the power curve as a function of delta, so let me now put a subscript for this delta because there is another delta now. We are going to call this delta P, where delta P is the power angle. Completely different from the torque angle because this is the angle between the terminal voltage and the back EMF space vector. Delta tau was the angle between the BMS space vector and BR space vector. It had nothing to do with the back EMF. So they are slightly interrelated, as you can see. But from this equation, it's completely different factors. The angle between the V and the E. Okay. So we have delta P. Let's plot this. And on the y-axis, let me plot the power. And the curve looks exactly same as a torque curve. So what does this mean? 90 degree being the maximum power that can be generated, delta P being 90 degree. This is when the power generated by the motor is at its maximum. If you were to go on the right side of it, then you would end up generating lower power. On the left side of it, you'll end up generating lower power. So let's go back and analyze the stability of this. Let's say your rotor is rotating at some speed and your motor is asking for some torque. So in some equivalent power, P1, and this is going to be at some angle delta P1. And if the load suddenly asks for higher power, then you would jump ahead. Same logic, because you draw power out of the inertia, which means the speed has to come down. You're drawing energy out of the inertia because the power on the load side is higher than the power on the electrical side. So the rotor slows down. That means the angle between the rotor angle and the stator starts to lag behind. Delta increases. The same logic comes here. Delta would increase, and you would go to a new position, delta P2, where you would generate higher power. If this power now satisfies the load demand, this would be your own new stable operating point. And this can keep on happening until you reach this point. If you were to exceed this, then as you demand more and more power, you start lagging further and further, and your power generated will become lower and lower. So this is the power you demand, but this is the power it can generate. So the deficit will reduce the rotor speed even further temporarily, which will make it lag behind, which would then make it produce even less power, which will increase the deficit, which will make it lag even further behind until it comes to a full stop. So this is the maximum angle between the EMF, the back EMF, due to the rotor magnetic field and the terminal voltage that's applied. If it exceeds 90 degrees at steady state, the motor will come to a full stop. It cannot exceed this angle. How about if it exceeds in the first case? So in this case, V is fixed. Omega E is fixed. In our first case, so this is our second case, describing delta P, power angle. In our first case, when we looked at the torque angle, delta tau, tau M, we got the same curve. This is again with respect to torque, this is with respect to power. So here we have I fixed. And again, omega E may or may not be fixed. But just to keep it simple, let's assume omega is fixed as well. So for a given current, this was the torque response we got. But the 90-degree limit there comes from the fact that for the given current, that's the maximum angle above which if it goes, it will become unstable. But if you are applying a fixed voltage and not actually fixing the current, then you can operate at a point where the torque angle is greater than 90 degrees. Because this is a curve for one particular current. Let's say this is for some current I1, some current magnitude I1. If you were to say increase your current, then you will get a completely different curve with a higher magnitude. As your load angle increases, goes past 90 degrees, only if your current is fixed, you will have a constraint that you have to trace along this particular curve. But if your current is allowed to vary, your voltage is fixed, but your current can vary, then you can go to a higher angle, but your current can increase as well. Right? So you can operate in a new angle. So let's say your torque demand was here. For this particular torque curve, for this particular current, then you can't produce more torque than this point. But if the current is allowed to change, it can go to a new load angle which is greater than 90 degrees and go to a point where there is current that is increased, which can produce the torque that is being demanded by the load. So in the simulation that I posted on Canvas, you can clearly see that as you keep increasing the load torque, you can see that the angle between BR and BMS phase vector can in fact go past 90 degrees. But what can't go past 90 degrees is the angle between the EMF and the voltage phase vector. So this is a very common point of confusion, because there is another angle that I'll introduce in just a minute, which will show that the angle between the lambda S stator flux linkage phase vector and the BR cannot exceed 90 degrees. But a lot of people tend to confuse that angle with the BMS and the BR phase vector, which are two completely different things. This angle cannot exceed 90 degrees, this angle can exceed 90 degrees, and you can see that in the simulation that it can very well exceed 90 degrees. But the condition being that the voltage is the one that's fixed and the current is allowed to vary. If the current is fixed, then this angle definitely can't exceed 90 degrees. Okay, so let's look at the case. Let's complete the space vector diagram that we have here. So for the simplified circuit where we don't have any resistance, we have j omega LS drop, which should be 90 degrees along ESC. sorry, IS. So IS is like this. So J omega LS would be along this direction, which should be added on top of EMF. Oh, this much better. So this is going to be J omega E LS times stator current, and this net sum of this plus this is going to give you your terminal voltage space vector. And this angle is your power angle delta P. And this is related to how your generators will operate. Sometimes it's called the load angle as well. Even the torque angle is sometimes referred to as load angle. That's again a very big point of confusion. Because the way the generator would operate in a grid is as you have a generator which is connected to some load on the grid side. As the load starts to increase, so as the load starts to increase on the grid, your energy would be drawn out of the inertia. Same mechanism as we saw. Similar to how when you increase your load torque, the inertial energy is drawn. All the same thing would happen when you increase the load torque on the grid side as well. On the electrical side of the generator, you put some load on it. It is basically going to ask for more power on the electrical side. And that power would initially come from the inertia. And then the motor would start to slow down. And then the angle would start to increase between the rotor magnetic field and the stator magnetic field, which would also then increase the angle between the EMF and the voltage V. Why does that happen? Because if this one goes behind, then the EMF will also go behind. So as this one drops backwards, EMF will also drop backwards because the angle between EMF and VR is always going to be 90 degrees. So as this goes backward, the delta P will also increase. As delta P increases, the power can be generated by the generator and transferred onto the load, onto the electrical grid would increase. And once it satisfies the new power demand on the electrical grid, it would now settle to this new angle. That's the reason they call it load angle. When you apply an added load onto your electrical grid, basically this is the angle that increases. And even when you look at it as a motor, the same thing happens when you apply mechanical load on the motor. The rotor angle the torque angle start to go behind, and that again starts to increase. And that's another reason they call that angle also load angle. The term is somewhat used interchangeably that causes a bit of confusion. Okay. So now let's account for the fact that let's bring in the resistance. Actually, before we do that, before we go to the practical circuit with the resistance, let me introduce one more term. Let's erase this. So we have two magnetic field, BMS space vector and the VR space vector. If you take some kind of a measuring device, let's say you have an Hall effect sensor, and you put it in the rotor air gap, in the motor air gap, and you measure the magnetic field at different points in the air gap. The value that you'll be measuring would neither be BR nor be BMS, right? It will be the sum of these two. Because in a permanent magnetic signal motor, both of these magnetic fields exist at the same time in the air gap. So the sum of these two fields is what is going to be that you can measure. And assuming that nothing is saturated, in an ideal case, superposition applies. So the net magnetic field you measure in the air gap would be the vector sum of these two. Let's call this BA space vector. So this is the net magnetic field, that's the air gap. And let me make a statement here and then we'll see why that is the case. The angle between these two would be the same, delta P, as the angle between the back EMF space vector and the terminal voltage space vector. So this angle and this angle would end up being one and the same. In the case where, again, this needs to be made very clear, where R is equal to 0. So for that case, delta P, angle between V and E would be the same as the angle between BA and BR, the net magnetic field in the air gap and the magnetic field in the rotor. So let's look at what the reason for this is. And along this direction would be the vector for, we haven't introduced this term, but this would be used in any vector control textbook, would be the term lambda S. So BA is the air gap B field due to BMS and BR. So this is equal to BMS plus BR, vector summation. Lambda is the flux linking the stator winding due to both BMS and BR. So we already seen this term flux linkage. We did use this when we derived the EMF equation for one of the coils. Actually, when we derived the inductance equation, we did look at what the flux linkage term was. So it's the same term. And how do we go about deriving it? We basically looked at the magnetic field at every single point in the air gap. And then we looked at the conductor density that we are interested in. And we figured how much the B field is linking each of these coils. We took some delta theta, some amount of conductors, the incremental amount of conductors, and we figured out the magnetic field that's perpendicular to it. And basically did an integration for all angles, 0 to 2 pi, to cover 0 to pi to cover all the set of windings that are there. And that ends up giving us flux linkage. So how do we find out the flux linking due to both BMS and BS? Basically look at the BA, which is the magnetic field in the air gap due to both BMS and BS, and then figure out how this BA couples to the sinusoidally distributed winding of the stator conductor. And then you do this integration over 0 to pi, you get the total flux linking that one. Now the value of that would have to be along the same direction as BA, because the only vector entity in that whole arithmetic is BMS and BR. Rest is all just integration, and the conductor density and all of those do not alter this factor. So the flux linking the stator conductors would be along the space vector for that would be along the same direction as the net magnetic field in the air gap. Some textbooks refer to this as BS space vector, which I think is not the right way to call it. Lambda S is right though, because the flux linking the stator windings, its contribution from both BR and BMS. But BS gives a false idea that it's somehow the magnetic field due to the stator current, which is not. Magnetic field due to the stator current is BMS, and the magnetic field due to the rotor magnetic field is BR. Some of these two is the magnetic field in the air gap, which some textbooks refer to as BS, and this has been quite a bit of confusion as to why the angle in Professor Mohan's textbook is delta for BMS and BR, while other textbooks use this, and a lot of people think that's somewhat wrong, but I think this is a much better notation rather than this one. Okay, so we'll stick with this one. So this is going to be an angle, and let's see why this delta P is same as this delta P for the case where RS is equal to 0. So let's go back to our equivalent circuit. LS, some back EMF, and some VS. How did we get this back EMF? This was back EMF due to BR. And how did we get this? We basically looked at the flux linking each of our stator coil, flux linking the stator coil due to BR, and then differentiate that flux linkage to get the back EMF E. Now we can do the same thing for this as well. You can look at the flux linking d lambda S stator due to BMS and differentiate by dt. And that should give you the voltage that is EMF that's induced across the stator coils due to the varying magnetic field of the stator induced currents. So the voltage across this is going to be given by this equation. But we already know the voltage across this from our phasor representation. That would be J omega E times Ls. So what is going to be the net EMF between this and this? There are two ways you can calculate this. So the net EMF between this and this, E net, is going to be equal to, the first way is basically summing this and this term. So d by dt of lambda stator due to BR plus lambda stator due to BS, which is the same as saying it's lambda stator due to BA, which is what we have indicated as just lambda S. So this whole term is just d lambda S divided by dt. And the other way of doing it is what we have been always doing, which is basically taking this EMF due to BR and adding up the voltage drop across this inductance, J omega E Ls. So both of these should give us the same value. So let's go back to our diagram here. Our EMF plus j omega E LF is the net EMF across the stator coil, which are in the absence of resistance. So which is then the same as the terminal voltage Vs. Right? And this again is the same as the terminal voltage Vs. And which is what we have here, the terminal voltage Vs. If you want to put the subscript. So this is the net terminal voltage. So again, this is due to Br. That's why it's at 90 degree from Br. Now, if Vs is d lambda s by dt, what will be the angle between Vs and d lambda s? Same as the angle between, let's say the inductor, you have some current I, the voltage across the inductor is L di by dt. So the angle between the current and the voltage will be 90 degrees. Same thing happens, right? The current lags the voltage by 90 degrees in inductor because it's di by dt. Same thing here, V is d lambda by dt. So the lambda would lag Vs by 90 degrees. So the angle between lambda s, which is same as the net angle between the angle of the net magnetic field in the area and the voltage space vector. So the angle between this and this must be 90 degrees. So this and this is 90 degrees. So angle between BA and B is 90, angle between E and BR is 90, angle between E and BS is delta P. Then of course the angle between BA and BR must also be delta P. Because then this and this angle would have to be same as this and this angle because of the 90 degree relationship. So this and this angle would have to be the same. So the angle between BA and BR would be the same as the power angle between the back EMF due to BR and the terminal voltage Vs. There's again one more point of confusion whether back EMF is only this term. No, not at all. Whether the EMF is only this term, not at all. This is the back EMF because the rotor is rotating and the rotational motion creates an EMF, and that we typically call the back EMF. The voltage that's induced across this winding, that is also EMF. It's not back EMF, but it's an EMF because it's created by the varying magnetic field due to the stator currents. That again is the EMF. It's an induced voltage. And the sum of these two voltages, the net EMF that develop across the stator coils, and which is what would be this term plus this term. Let's look at the case where we introduce the resistance as well in our equivalent circuit. And this will modify the angle just a little bit. So the minute we add a resistance here, some Rs, our space vector diagram changes. Right here. So the minute we add some resistance, this is no longer a space vector diagram. For this portion. So this is E due to Br. And then you have some drop due to the stator resistance, Is times Rs. And then on top of that, there is j omega E Ls. And the sum of these three is now your terminal voltage V. And the angle between these two is the power angle. Now this delta P is no longer going to be same as this delta P. Because this term on right here, this d lambda by dt is no longer equal to Vs. Well, what is it going to be? The d lambda by dt is this voltage right here. But there is an IR drop before it becomes Vs. So it is going to be Vs minus Is Rs. What your d lambda dt is going to be. And that is where your VA space vector is going to point at, where lambda is going to be pointing. So the angle between the VA space vector and the lambda space vector is no longer 90 degrees. The angle between the Vs minus ISRS space vector, if you subtract that out, then that space vector would be at 90 degrees from lambda s. So this angle will be still delta P because that's a power equation, but this angle is no longer delta P, right? You can just call it some other delta. Let's call it delta L. But this angle would start to deviate from that particular angle. But the angle at which you can still get the maximum power is now a little bit tricky, because if you're thinking of the maximum power coming from the terminal voltage, that would be when this delta is equal to 90 degrees. But not all of that power goes into the mechanical system. Some of that power is actually dropped out to the resistance. So you have tiny amount of power that's being dropped to the resistance. The maximum angle at which you would get the maximum power going to the mechanical system is not going to be 90 degrees, it will be slightly a little bit of a lower angle. But still 90 degree between EMF due to BR and the voltage will be the point at which if you exceed about for a fixed voltage, your motor will completely comes to a stall, because the power going to the motor far exceeds, is far lesser than what the load torque is demanding, and then the rotor will come to a stop. These are the three angles, and then final term is the load angle So those are the three angles that cause quite a bit of confusion, but hopefully it should be clear. Okay, so with that, let's go to the second topic where we want to design the motor model. So let's write down all the equations first for a permanent magnet synchronous motor. Okay, so let's see. Let's start out with the easy one. Your tau m minus tau l, tau m minus tau l must be equal to your j d omega by dt plus b times omega. So this is a mechanical model which we have been using from, I think, lecture 3 or something. So I'm not going to go into details of this all over again. So this is going to be an equation. We have an expression for electromagnetic torque. Tau em is pi times r times l times ns time divided by 2 times the rotor magnetic field space vector times the current in the coil times sine of delta. Now finding out the sign of delta term is all unnecessary. So there is another way of, the way we got this expression when we derived in class is basically we figured out the torque due to each of the individual phases, which ended up coming out to pi RL NS divided by 2 times BR space vector times, let me think about this. So it was times IA as a function of time sine times sine of delta, then tau b was again pi RL ns divided by 2 times br times ib of t times sine of delta plus 2 pi by 3. If you have forgotten how we got this, go back and look at the previous lecture. By I think lecture 25 maybe, ns by 2 br space vector ic of t times sine of delta plus 4 pi by 3. And we saw that once we substitute sinusoidal currents here, these two products would end up being some sinusoidally varying term if the speed at which this delta is changing is not the same as which the speed at which the currents are changing. If those two terms are not the same, then we saw the net torque would be 0. If they are changing at the same speed, then there will be a torque produced, but the torque would have a highly oscillatory component to it, which is what makes one-phase permanent magnet synchronous motor very inefficient. You can get a permanent, once you get a permanent magnet synchronous one-phase permanent magnet rotating, it can continue to provide sustained torque, but it will provide an oscillatory torque. There is an average DC component and there is also an oscillatory component, which makes it very noisy and very inefficient, and it will damage the battery quite easily. That's why you don't typically see a permanent magnet synchronous motor that's one phase, because if you are good enough to spend money on putting a permanent magnet on the rotor, then you should have money to put 2 more phase coils and make a proper motor. Okay. When you do an induction motor, that's not the case. You do make very cheap induction motor where you don't want the extra added cost of putting a magnet on the rotor, and you just use these copper aluminum bars, aluminum rotor bars. You don't even put copper because copper is slightly more expensive. So you put these aluminum bars and then you don't put any rotor magnets. In those cases, you would do one phase because you don't want to have the added cost of putting a 3-phase coil. You would use some tiny, very thin conductor to create an auxiliary secondary 2-phase system, which would shut off immediately after the rotor starts rotating, so that the coil doesn't burn out. It's a very thin wire, copper wire. You don't want to waste money on it. To get a permanent magnet, if you're willing to put a magnet, you might as well put 2 more coils and make it a 3-phase. But these were the torque due to each of the individual phases. Once you sum these torque up, you get the total electromagnetic torque right here. So the same thing as for the EMF as well. EMF for the A phase comes out to be pi times R times L times NS divided by 2. Oh, again, these currents, I should be careful. Coil currents. NS by 2 times BR space vector times 2 by p times, or let me use that term in the end, times omega mechanical times sine of delta times 2 by p. So this is the coil EMF. And same thing for B phase. Pi RL NS divided by 2 VR magnitude omega mech sine of delta. Look at that extremely same repeating pattern, except for this 2 by p, which in a minute will disappear. So this again is coil current of B phase, coil current of C phase. EC is again same thing, pi RL NS by 2 VR's magnitude omega mechanical, not electrical frequency, sine of delta plus 4 pi by 3 times 2 by p, which is the pole pair, inverse pole pair, same coil EMF. So we have 3 EMF, 3 torques. I think we have everything in place. So before we jump ahead, let's see what these coil currents are. In case of a 4-pole motor, a pole pair, basically we had this motor. We had a bunch of conductors here. Let's say it's created the north pole, and another bunch of conductors here which created the south pole. And same way this one, let's say, created at one particular time north pole, and this set of conductors created a south pole. As time goes on, of course, these structure would have to rotate around, also we create rotating fields as the current changes in time. Okay, so this is what we have for one particular set of coils. Now what the coil, so we can represent this as one set of coil. Let me call this group. Let me indicate it with the diagram like this. That whole combine north and south together. And this group, I can draw with another equivalent coil. Now I have the option of either connecting these coils in series for a single phase. So this I'm just talking about A phase for a 4-pole motor. Similarly, I have B and C and all those. And that again, whatever you do for the A phase, you would have to do the same for B and C as well. If you connect these in series, if you have the same set of winding distribution for the B and C, it would make sense to connect them in series as well. Otherwise, you will get uneven flux distribution in the air gap, which would then make your space vector not go as pure, nice, fixed magnitude. You will get an elliptical shape, the space vector will trace instead of a circle. Right? So either you can connect this in series like this, or you can connect these coils up in parallel and bring the terminal up. So this will be the A terminal, this will be the neutral terminal that gets connected with the other 2 phases. So the other 2 phases would be like this as well. So you will have your B phase, and then you will have your C phase. So this would be your B, this would be your A, this would be your C. These 3 terminals come out. These 3 terminals are shorted and just buried inside the motor. This would be the 4-volt case. When you have 6-pole case, you have the option of putting these coils again in parallel, or you have the option of connecting these coils in series. Now, when you get to 8-pole case, you can do something a little bit more interesting. So, in case of an 8-pole case, you have multiple configurations. So, you can have the 4 pole pairs in parallel. You can have the 4 pole pairs in series, or you can have 2 of them in series and 2 of them in parallel. Of course, you wouldn't want to do 3 of them in series, 1 of them in parallel. That will again make it an asymmetric distribution, which would then cause the space vector to be not trace of the circle. So there are 3 possibilities. When you go to higher number of poles, you have more combinations that you can create out of them. So, irrespective of number of things, let's classify this with 2 terms that we are going to introduce. My all markers are so shitty. Okay. So we are going to introduce a new term, number of parallel paths, and then number of series pathways. In this case, the number of parallel pathways is 4. Number of series pathway is just 1. And in this case, the number of series pathway is 4. And the number of parallel pathways is just 1. There is one network in the circuit. In this case, the number of series pathways is 2, and the number of parallel pathways is 2 as well. This measures NP, this measures NS. So number of coils in series and the number of coils that are in parallel. So here the number of coils in series is 4, number of coils in parallel is just one set. Here the number of coils in series in each pathway is 1, and the net number of parallel pathways is 4. Right? So these are the terms that we are going to be introducing. Now let's look at what the coil current is. If the current in the terminal of the motor is some IS, the coil current is going to be equal to the current in the terminal divided by NP. In this case, divided by 4. In this case, it's going to be IS divided by 1. In this case, it's going to be IS divided by 2. So where are these terms coming from? It's basically the current in the coil is going to be the current in the terminal divided by the number of parallel paths. Okay? When it comes to EMF, so this term, we can replace it with IA of T divided by the number of parallel paths, where IA itself now becomes the terminal current. IA term is the terminal current. AC divided by NP. Okay, now let's come to the equation for our back EMF. So back EMF is this is the voltage developed across each coil. Now let's look at the case for the coils that are in parallel. In this case, all the coils are parallel. If this generates some voltage E, then the net voltage across this parallel coil structure would still be E. Right? The net voltage is also E because these are parallel voltage sources. Now if you connect these in series, so this is 10 volts, 10 volts, 10 volts, 10 volts, you put all 10 volts in parallel, the net voltage is again 10 volts. But here if you have E, and E, if you connect them in series, the net voltage is 4E. In this case, you have 2 in parallel, 2 in series, so the series would cause 2E, this would cause 2E, 2E parallel, net voltage is again 2E. So what is the equation for the coil, the net EMF, terminal EMF compared to the coil EMF? E terminal is equal to number of series coil times the E in the coil. So this one, you multiply by NS, multiply by NS, multiply by NS. Now it becomes a terminal EMF. Alright, fantastic. In the beginning of, I think last class, I told you that the coefficient scaling the torque and the coefficient scaling the EMF, let me put capital term indicating its terminal now. And tau in capital is just same symbol. I told you that the terminal, the factor scaling the EMF must be the same factor that's scaling the torque. Right? Again, because the power balance requirement, the mechanical output power must be same as the electrical power, and that can only be satisfied if this term have the same coefficients, Ke being equal to Kp. But clearly here we have two different factors scaling. We have some Ns times 2 by P, and then we have divided by Np here. So where is the missing terminology coming from? So let's go back to the scale and see if there's some kind of relationship between Ns and Np. Let's take the Ns Np product. In this case, we have Np, Ns equal to 4. In this case, again, Ns Np is equal to 4. In this case, again, Ns Np equal to 4. Just some easy logical thinking, you can see quite straightforward what is going on there. Ns times Np must be equal to the number of pole pairs. Because in this case, we started out with 8 poles. So the number of pole pairs were 4, 8 divided by 4, 2 being 4. So we had 4 coils. And we distributed these coils in such a way that some of them are connected in series, some of them are connected in parallel. When you take all the combinations, that total sum must be equal to P by 2. And all the combinations can, of course, be reversed by getting Np times Ns. Right? Number of possible series parallel pathways, number of possible series pathways. You product them up, you would end up with your same pole pair again, because that's the number of coils you started out with from the beginning. So from this expression, your Np, let me substitute for Ns. Ns is P by 2 times 1 by Np. P by 2 times, oh yeah, that's right. So let me substitute for Ns here. P by 2 times 1 by Np. So P by 2, 2 by P cancels. You are left with 1 by Np. So this one goes away, 1 by Np. This one goes away, 1 by Np. right? Same factor as we have here. So pi RL, NS divided by 2 times BR divided by NP. Same here. Pi RL, NS divided by 2, BR divided by NP. So same coefficients you get for KE and KT terms. If at all you get an expression when you model your motor KE being different from KP, there is one possibility that you don't have the same base, SI unit. So if you have the same units, so let's say you have your KE as some line-to-line voltage RMS per RPM. Typically, that's the normal value that's given in data sheet, and KT as some Newton meter per ampere. Of course, these two terms won't match up. Or let's say you had KT in some terms of pounds per pounds meter per ampere or something, right? Not in SI units. Then these two terms will not match up, of course. Like otherwise, data sheets, you will see these two terms different. But if you convert them both into SI units, Newton meter per ampere, and this one volt second per radian, where the voltage is the peak phase voltage, then these two terms will always have to be the same with respect to what motor you're talking about. Right? So now we have all the equations. Let's go ahead and model our motor in numericals, like a Simulink or something like that. So keep in mind this equivalent circuit. This is what we are going to be drawing, but I need the full board space, and I'm going to delete this. Okay, so let's start off with the terminal voltage. We have some terminal voltage. From this terminal voltage, if you subtract away the back EMF, maybe we might have a little space to draw it here. Resistance, inductance, leakage, magnetizing, LLS, LM, EMF, so VS, RS, ES. Again, in the lecture 25, I think I derived 26 or 25, we derived this expression where this one is LS plus LM times IA plus minus 1 by 2 LM IB minus 1 by 2 LM IC, which ended up coming out to be, oh no, sorry, L self, which ended up, there was a big mistake, L self, which ended up coming out to be LLS plus 3 by 2 L self times IA, which was same as LLS plus LM times IA, which is LS times IA. Right? So the same thing happened for lambda B as well. The same term with IB, the same term with IC, the same term with IA, and this ended up being LS times IB. And same thing for lambda C, same term with IC, same term with IEA, same term with IB. This ends up being LS times IC. So I'm going to retain this original form just because it looks pretty and we get to use a little bit of matrix. But there's another reason as well. When we do induction motor model, when I do the extra lecture for induction motor, this model becomes quite helpful because the inductance of the rotor keeps changing, and putting it in this matrix form becomes quite helpful. When we go there, you can get an I6 cross 6 matrix in that case. Okay, so we have our terminal voltage. We subtract our back EMF. We don't know how we'll get this back EMF just yet, but just leave it hanging. Terminal voltage is given to us 3 sinusoidal voltage sources, and we will put those 3 values here. Take a sine wave in MATLAB, and the angles alone phase shift by 0, 2 pi by 3, minus 2 pi by 3, minus 4 pi by 3, and put some magnitude for the voltage. Subtract the EMF. What you're left with is the voltage drop across this whole thing. We can first take out the voltage drop due to the resistance. So we have positive, negative, some resistance RS, and then the currents, all 3 currents, IA, IB, and IC. All 3 signals mixed together, multiplied by RS, subtract from the three voltages. So again, these three voltages are three values: VA, VB, VC, and this is EA, EB, EC. Instead of putting each of them separate structure, we can just mux those signal together so that it's a single nice diagram. So once I take this voltage, subtract this, what I'm left with is the voltage drop across the LS plus LM. Now what I can do is I can directly divide this voltage that I get by this inductance value and then integrate it, and I would end up getting the current. But let me instead use this model and then we'll try and see how it differs. Okay. So here, let me put this in matrix form. So your lambda A, lambda B, lambda C is going to be equal to LLS plus LM minus 1 by 2 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 LM LLS plus LM minus 1 by 2 LM minus 1 by 2 LM LLS plus LM times IA, IB, IC. Right? So this is my inductance matrix. Let me see what's a good symbol. Let me call it some double dash L. So this is going to be my inductance matrix. If I know my flux linkage and I multiply by the inverse of this inductance matrix, I will get my currents IA, IB, IC. Right? So this is basically, if you take this voltage minus the drop across this minus this voltage, all you're left with is the voltage across the inductance. Now what will be this voltage? This will be d lambda divided by dt. The flux linking this coil, the rate of change, the rate at which the flux linking this coil due to its own current is varying is what is producing the EMF across this coil. So if I subtract all of these terms, what I'm left with is the voltage across this coil, which is going to be equal to the same as d lambda by dt. And what are those lambdas? Those are the lambdas of each of those coil windings without any influence from the rotor magnet. So I have this flux linkage, I divide it by the inductance matrix, I would end up getting the current. So this is going to be d lambda ms divided by dt. So this is purely due to the stator currents, BMS space vector, the BMS magnetic field, not due to BR, because BR is captured by the CMF. Right? We are worried about this CMF. Okay, so we have d lambda by dt. You integrate this, you end up with lambda ms, and that's exactly what this is. Lambda ms, which is lambda A, lambda B, lambda C, and then you divide this by the matrix that I have written there. So this is a 3 cross 3 matrix. And the output of this is going to be a currents. IA, IB, IC. Right? The three currents that we have. I did it a roundabout way because I wanted you to get an idea of this inductance matrix. It's a pretty one. But you could have instead directly taken these lambdas, right, that you get here, divided it by 3 by 2 moves. I keep making this mistake. L self, L self, self, self. Instead of using the self-inductance matrix plus the linkage component, I could instead directly divide the flux linkage terms. An alternate way of doing this later. Let me draw it on the side. So once I get lambda ms, I can divide this by directly a scalar entity 1 divided by LLS plus LM. And here it's LM definitely, right? Basically this term, LLS plus LM. And that would give me the currents IA, IB, IC. And this would be lambda A, lambda B, lambda C. So I could have taken this divided by a constant factor 1 by LLS plus LM, and I got the three currents. But intentionally put it in this form because once we go to induction motor, we we'll use the same matrix, 2 3 cross 3 matrix that do not vary, and another 3 cross 3, 2 3 cross 3 matrix that varies with time. That will become much more intuitive in a matrix form. So I just want to introduce this early on. Okay, so once we have the current, we can close this path. Fantastic. Now again, going back, why are we putting it as integral equation instead of a differential equation? We could have set this equation in such a way that we had lambda, we have the current, and then we differentiated blah blah to get your EMF. But numerically, we already saw the stability of integration is much more stable compared to a differential operator. Right? That's the reason we want to go with integral operation when you do numerical simulations. Okay, so we have our currents. Once we have currents, we can get the torque. So a torque equation. So let me define this term. Let me define it here. Let me introduce AT is going to be equal to 5 RL ns divided by 2 times VR space vector times winding some factor. Let's call it some gamma tau, right? Which gamma tau is basically just going to be number of series connected coil. Maybe I can just replace that with number of, inverse of number of parallel connected coils. Because the current is going to split across these coils, so the NP factor gets introduced. Let me write down the KE value as well, which is pi RL ns divided by 2 times BR times 2 by P times number of series connected coil. This product must again be same as 1 by NP. So that KE and KT are one and the same. Just for the math of it, I'm putting the two separate equations to get an intuitive feel for it, but they should come out one and the same. So once we have the currents, we can dot product with the three values, sine of delta plus 2 pi by 3, sine of delta plus 4 pi by 3. We don't know what the delta is yet, but let's say we have that somehow. So you can have a sine block, okay? And this itself, you can offset the values by 0, by 2 pi by 3, use an offset block, plus 4 pi by 3, and the input of this would be delta. So you take delta plus 0, delta plus 2 pi by 3, delta plus 4 pi by 3, take the sine of it, so you end up with sine of delta, this is the equation that we have right here. Let me turn the camera. So these three equations that we have here, sine of delta plus 2 by 3, sine of delta plus 4 by 3, we still don't know what this delta is. I'll get to it in just a second. Now, by the way, this is the delta tau, right? This is the torque angle. We have the torque expression on that side. So this is the angle between the BMS space vector or your stator current space vector and your rotor magnetic field. So this is the delta tau. Okay, so we are basically computing these three. This factor is captured in our KV value, and now we have our currents. These are the terminal currents. That's why we changed it to terminal currents and instead of putting it in coil currents. Okay, let's go back to our equation here. So we have these terms, and the output of this is going to be, if you sum up all the three torques of each of the phases, you get the total electromagnetic torque tau EM. And once you have the electromagnetic torque, you already have everything we need. Positive, negative, you subtract the load torque, you subtract the drop across the resistance, the friction, and you integrate this, divide by the inertia. This would give you omega mechanical. Basically, the top equation that I presented. Tau em minus tau L minus b omega is equal to j d omega by dt divided by j integrated, you get omega mech, and you use that omega mech here. So we delete this. Now once you have omega mech, you can take this angle, you take this, integrate this, you will get theta mechanical. You multiply this by p by 2, you get the theta electrical. But the theta electrical is not the same as delta in our case because of the way we chose our delta. If you go back and look at the lecture 25, we chose a delta to be in the opposite direction of rotation. We are assuming the space vectors are rotating like this, we are measuring the angle delta along this, because delta, the load angle, torque angle, power angle are always defined as between the vector that's leading and vector that's lagging with the magnitude positive, just by normal convention. But the way we have derived everything in all our measurements, the opposite way of counterclockwise rotation is considered positive. So this is a negative measurement. So again, in the model, I put the negative gain here, and I've given an explanation as well in the Canvas model that I posted. And once you do this, basically that will give us our delta angle. Basically, at time t equal to 0, our current space vector was like this. Our VR space vector was along this angle. The angle between them ends up being delta. And this is basically the rho triangle with respect to the stationary reference frame, the alpha A phase coil. Right? This is where we have our 0 degrees. Okay. So this loop is closed. Now we need to close the back end of loop. This product times KT. I missed the KT here. The output of that is W. Now, if you look at the back EMF equation, we have the same equation for the back EMF, except we have a key term multiplied by omega 10, omega max. But this term is same as what we had in the torque equation. So we're going to use the same thing, just extend it. Let me take this term and then multiply it with omega max. The output of this K by KE, which should be same as KT, and the output of this would be a back EMF E, which consists of all the three back EMF. With it, we are done with the model. So we take a voltage, subtract back EMF, subtract the resistance drop, you get the d lambda by dt due to the BMS magnetic field. Integrated, you get lambda flux linkage, the stator coil due to its own magnetic field, divided by the inductance matrix, you get the three-phase currents, multiplied by the torque constant and the individual phase torques, dot product, basically IA times this, IB times this, IC times this, and summing it up. That's what dot product is for two vectors. Right? And then the output of that is electromagnetic torque, subtract the load torque, subtract the B omega drop, divide by J, integrate, you get omega mechanical. And then once you get omega mechanical, integrate, you get theta mechanical, multiplied by the pole pairs, you get theta electrical, inverted, you get delta because of the way we are measuring the angle. And then the rest of it is just closing with the loop on its own again. One term that I haven't introduced is the formula for inductance, which you have derived before. So L self is mu naught pi RL. NSP, NS is the number of turns for a single phase. NSP is the number of turns per phase per pole pair. Per pole, sorry. Pi RL, mu naught pi RL, NS divided by LG. Mu naught pi RL, NSP square divided by LG times 2 by T. So this is going to be your self-inductance. And then you need to do 3 by 2 times to get the LM value. In the L matrix, we don't use LM, we use L self. Now this inductance, so this is the inductance of a coil of a single pole pair. If we connect those coils up in series, if we have number of series connected coils is NS, then the net self-inductance is going to add up. So it is going to be NS times L self. And instead, if you have these coils in parallel, with the number of parallel pathways being NP, then L self is going to be inductance divided by NP. Think of it as parallel resistors. The net resistance would be RP, the resistance divided by the total number of parallel pathways. If the resistance are the same happens with inductance. Now, if you have a bunch of connections where there are a bunch of coils in series and another bunch of coils in parallel, then the net self-inductance is going to be equal to L self of coil. You're going to have L self of coil, which is what our formula here is, times the number of parallel pathways divided by the number of series pathways. Sorry, number of parallel series coils divided by the number of parallel pathways. Depending on how we connect this coil, this inductance term L self that I've used here is obtained in our model. Then we have every single term. We have our KT, we have our KE, we have our KP, and we also have our inductance matrix that's needed. So once we get all of these, we can get our omega mech, we can get our angle, delta angle, and this delta angle, the way we have defined it, in our equations, that is delta tau. So this is going to be delta tau. So to figure out what these angles are, I've written a separate script in the MATLAB file that I've uploaded on Canvas page. Run that script to create all the plots. So what it basically does is, if you want the delta P, it will take the three voltages, compute the space vector by putting it in the space vector transformation, compute the three EMF, get the three EMF, put it in the space vector transformation, and figure out the angle between E and V. So the angle between E and V would be your power angle delta P. Now, if you want to figure out the angle between BA and BR, what it would basically do is figure out this voltage minus ISRS, you'll get some voltage, integrate that, and you'll get the flux linkage lambda. Figure out the space lambda S flux linkage, not just lambda MS. And the angle between lambda MS and theta electrical would be your delta between B air gap, lambda S and your theta E. That is going to be your delta L, which I indicated in one of the space vector diagram. And the delta that we have here, that itself is your delta tau, which is basically the angle between BMS and BR. So the same as angle between BR. So this is our delta tau. All these three angles will be computed, and when you run it, you'll see that if you say you want a fixed current in the model in the init file, then when delta T becomes 90 degrees, later it will become unstable, left hand side will be stable. If you say you are applying a fixed terminal voltage, delta P becoming 90 degrees is the point where the motor would have maximum amount of power produced going in from the generator side, above which after 90 degrees the system would become unstable. When this reaches 90 degree, delta tau would be well past 90. In the model that we have, it goes to about like 125, 130 degrees. Okay, so with that, we are done with the permanent magnet synchronous motor model. Let's quickly look at the Simulink model that I have uploaded and just make sure it matches up with the diagram that I have on the left there. Okay, so here is the motor model. And if you double click on this model, you should see the exact same equation that I've written down there. So you have Vs minus Es, and then you subtract the voltage drop across the resistance. That'll give you d lambda ms by dt. This is just the flux rate of change of the flux linking the stator coils due to the stator currents alone, not including the BR magnetic field. You integrate it, you get the flux linkage, and then you divide it by the inductance matrix, which is just a constant matrix. You get your currents. Again, here you could have just replaced it by dividing by a scalar factor 1 by L self by SLL. But just to keep it interesting, I put this matrix form. You get the three currents. Multiply the current by the sine of delta plus 2 pi by 3, sine of delta plus 4 pi by 3. So IA times sine of delta plus IB times sine of delta plus 2 pi by 3, IC times sine of plus IC times sine of delta plus 4 pi by 3. Sum them up and multiply by kT, that will give you electromagnetic torque. Subtract the load torque, subtract the B omega drop, divide by 1J, integrate it, you get the omega mechanical. And then you get the omega mechanical, multiply by P by 2, you get the omega electrical. At steady state, they will be the same as the grid frequency. And then integrate it, you'll get the theta M. And we invert it so that we get the alpha in our equation, which was effectively the delta that I have written on the board there, delta tau. And then once you have the delta tau, you basically put it back into this equation to get the torque expression. And you multiply this with omega mech, scale it by Ke factor, you get the back EMF, and then you close the loop all over again. Okay, so this model, once you run, you'll get all the results. Once you get those results, run this file, plot file, you get the plots of all the diagrams. But in the future, if you don't want to create this model, you just want an easy fix, you can directly drag and drop the synchronous motor model that MATLAB has. And the values for the resistance is the same as our resistance that we have per phase model. The value for the DQ inductance, and in this case, when we go to advanced electric drives motor, we'll see motor with some kind of saliency like an interior permanent magnet, where the inductance across one axis will not be the same as the inductance across the other axis. In our case, we are looking at surface permanent magnet with permanent magnet like neodymium, where it has the same mu r factor as you would have with the air gap. So every pathway has the same reluctance in effect. So our inductance is same along D and Q axis, and the value is going to be Lm plus Ln. When we do our advanced electric drive course, we will use again Professor Mohan's way of deriving the equations, which has power invariance. So there the LM that we calculate in the DQ will be completely different from the LM we have in our per phase model. So this again is a point of common confusion with a lot of people. But the way MATLAB does the DQ modeling, LM is the same as the LM in DQ as well as in the per phase model. But this also means the power calculated as the inner product of the DQ currents will not be the same as the power calculated as the per phase inner product. We'll have to use some scaling factor to do that. If you use power invariance transformation, then this LM would be different. It will have a root of 2 by 3 factor to it. So when you do this model in the future, if you're using the MATLAB pre-built model, just use LM plus LS here. And then the vacuum of constant, as I mentioned, they don't use the one that we have been using in the class, which is peak voltage divided by peak voltage second per radian. They instead use peak voltage, peak line-to-line voltage per kilo RPM. So that's where the scaling factor comes from. We go from peak voltage, phase peak voltage to line, you multiply by factor of square root of 3. And then this takes it from radians per second to kilo RPM. Most data sheet would again not use this. They would use VRMS per V line to line RMS per kilo RPM. That's what you commonly find in data sheet. So this is the factor you would use RKE that we got from our equation, scale it by square root of 2 root 3 to go to line from peak phase voltage, and then multiply by 1000 times 2 pi by 60 to go from radians per second to kilo RPM. And these are all your frictional constant and your inertia. And click OK and you run this model, you should get the same answer as you would get with this model that we have. If you scope a little bit and go and look under the mask. So if you go into the mask, I don't know who designed this model. It's unfortunately unnecessarily complicated. Even if you use DQ transformation, the model comes out actually pretty easy. Just a bunch of equations which can be simplified, all of this expression that's here. So it's unnecessarily complicated. When we look at DQ model, we will look at how to do this. But there is no need to do this model in DQ at all. Because at the end of the day, when you do DQ, you transform all these phase quantities that you have into a rotational reference frame. And pretty much similar thing is being done here in this multiplication going on here. So when you go to DQ model, you end up actually doing more computation for a permanent magnet synchronous motor model as compared to what you would get with an ABC model. So there is absolutely no use. And even in terms of stability, you don't gain any numerical stability by going to DQ model compared to this ABC model that we have here. So you can just stick to this model. But when you go to induction motor, we can clearly show that the DQ model has a little bit of more numerical stability compared to the ABC model. And also the computation is far lower. And when you have a DQ model for induction motor compared to a ABC model. If I have time, after the last lecture, I'll record one more video, two videos. One of them will be on one-phase induction motor. The other one will be, if I have time, I'll do it for the induction motor modeling. Otherwise, I'll do a full recording again when I do the advanced electric drives course next semester. You can take a look at it at that time.